So our next speaker is Dragana from EPFL, and Dragana is going to tell us about proving and disproving equivalence of functional programming assignments. So the stage is yours.
Right, so thank you for the introduction, and thank you everyone for coming to my talk. So my name is Dragana. I'm a PhD student of Viktor Kunčak at EPFL. And I'm happy to tell you about our work on equivalence checking of programming assignments. Before we start, because it's 9 a.m. here, I want to start with this warm-up exercise from an actual programming course. So the question is to write a function that removes duplicated elements from a list. So in Scala library, this is called distinct. I think it's similar in other languages. I will not ask you to actually write this now. I will show you one solution. And the question is to grade it, so to tell me whether this solution is correct or not. And we can look at the code together a bit. So there are three functions here. The top level function, unique, takes an input, which is a list. And then it delegates the main work to this function called distinct. It takes two lists. One is initially empty, so this is going to be our result. And the second one is the original list. And then we do this iteration on the original list. And every time we find an element that doesn't belong in the result, we add it to the result. And then to check whether something belongs in the result or not, there is this third function called isin. So is this solution correct? The answer is yes. And how do we know this? And how can we scale this question? So how can we answer this on hundreds of submissions in a programming course? That's the topic of my talk. So back to our title, here on one side we have many, so hundreds of submissions to programming exercises, and we have a reference solution, or a few solutions that are correct. And on the other side we have this classification of programs, so programs that are not correct with their counterexamples, and programs that are correct with those links that represent proofs of equivalence to one of the reference solutions. And here in between we have this verification component that is responsible for producing this output automatically. So it's really an interesting problem that combines a bit of formal verification, a bit of clustering. We saw those programs consist of many functions, so there's also this problem of decomposition into equivalent helper functions, and then those functions are typically recursive, which is also quite challenging for proofs of equivalence. Before I tell you how we answer all those questions, I want to ask a few more. So the first question is, why proofs? When we talk about introductory programming, why do we care about proofs? And my answer is that because testing is not quite enough. So testing works great for incorrect programs to give you those counterexamples, but it doesn't really give you any guarantee that programs are correct, right? So we need something stronger for this. We need formal verification. And then why equivalence checking? We just saw in the previous talk this formal verification is very hard, right? You need to write specifications, preconditions, postcondition. This takes time. This also takes expertise. So it's not really automated. So with equivalence checking, you naturally get this specification from the reference solution. So it's pretty convenient. Right. So now that we got this motivation out of the way, I can tell you a bit about our approach. So I will explain three main pieces of our work. And I will explain them bottom up. So first, I will explain this pairwise equivalence checking. So given two functions, how do we decide if they're equivalent? Then the second piece is this function called matching. So when you have programs that have many functions, how do we find equivalent functions among those programs? And then finally, once we know all of this, the final piece is this clustering algorithm that does this efficiently for many student submissions. So the first piece was this equivalence checking of one given pair of functions. And before I tell you how we do this, I should probably define it, because different people define the equivalence in different ways. So for us, we say that a pair of functions are equivalent if first they have the same signature and they both terminate, and then if for all inputs they return the same output. So it's just input-output equivalence. There are no side effects. And to show you how we automatically prove equivalence of functions, I have this example from the first slide. So if you remember, there was this final helper function called isin that just checks whether something belongs in a list. So I have a pair of functions here that do that. And to prove them equivalent, we use proofs by induction. And to be more specific, we use functional induction. So this is a function of on the body of the function that we are trying to prove equivalent. So let's say we take this left function here. This is, in a simplified way, this is actually our proof. So it's basically just this function with an extra post condition. How is this a proof by induction? Well, if you look a bit closely at this recursive call here, and if I unfold this call, I get basically the same code, just on the tail. And all the way down, I have this other recursive call now on the tail of the list. And because I had this post condition that should hold after I execute this recursive call, I can take it as an assumption. And so this combination of assuming that something holds for a tail and then proving that it holds for the overall list is exactly the inductive step in our proof. And this all makes sense because those programs are terminating, so eventually we will hit the base case, which trivially holds. Okay, so the second piece was this function call matching. So I have this mini example of two call graphs. And then we have this problem of finding equivalent pieces, so equivalent recursive functions among those programs. I can show you this on the same example. It's just the code is a bit large, so I cannot show you two programs side by side, but that's okay. I can extract their signatures, which is what we care about here. So we had three functions, if you remember. There was this top-level function, then first helper function, then second helper function. And let's say the structure is similar across two programs. And now we have this problem of finding, let's say, for isIn, a matching function in this other program. And for this, we use types a lot. So types are very helpful because if you remember, signatures have to match. So all those functions that don't have matching types, we can discard. And here for isIn, the only good candidate turns out to be this other isIn function. Types are also useful to align arguments across two functions. If they don't really appear in the same order, you can use types to restore the order. Sometimes we are not that lucky, and types don't quite identify our match or don't help us fully align the arguments. So here, for example, all the types are a list of int, all the two types in both functions. And so when types don't fully help, we also use tests. So what we can do is we can run those functions on some small inputs, and then if they don't produce the same output, we can discard those argument alignments or some pairs of functions, which further narrows down this search. Here I should tell you that this testing we just use to identify good matches, but not to decide anything. There is always this final verification step afterwards. And I should also tell you that for those tests, what's convenient when you deal with many submissions is that you can actually reuse counterexamples that you get from treating many submissions. And so here, user doesn't need to provide anything. We actually use counterexamples that we get throughout this algorithm. Okay, and the final piece was this clustering algorithm that takes many submissions that all have many functions and then has to classify them. So this is challenging because we want this to work in practice, so we want to achieve good performance. But at the same time, it's also a bit helpful. You saw that we can reuse counterexamples. We can also use the fact that equivalence is a transitive relation. So if you prove equivalence of some programs to a reference solution, then you can use those programs as new reference solutions to prove even more programs correct. So I can show you this on an example. It's an output of one of our actual benchmarks where we had one reference solution, which is here in the center of this cluster. And then on the right, you have a small cluster of programs that would all time out against the reference solution, but they turned out to be equivalent to another student submission that we could previously prove equivalent to the reference solution, and therefore they are also correct. What's interesting here is that this happens automatically during the work of this algorithm, and it also happens without checking for every single pair of functions. So we have this prioritization of solutions to get there in some reasonable amount of time. Right, and speaking of time and numbers, I can also tell you a bit about our evaluation. So the evaluation has two parts. We tried all of this on examples from equivalence checking literature and also from actual assignments from actual programming classes. And so I can show you some numbers here. So first, there's this small benchmarks from the equivalence checking literature. It has 17 pairs of equivalent functions that we extracted from papers on those two tools for equivalence checking. So I show results on those two tools, and I show results on our system. And those benchmarks are interesting because they are really from papers of those two tools, so they really show some tricky recursions. They are a bit artificial, but they're quite good at testing the limits of equivalence checking. So some of them show some examples where those tools work well, and some of them show limitations of those two tools. And so we were happy to see that our system actually does overcome the limitations and solves most of those problems. But as I said, those are a bit artificial. So we also evaluated our system on actual assignments from actual programming courses. So for this, we collected benchmarks from 3 tools for automated grading. There were originally no camel, so we went and translated all of this to Scala. In total, it's thousands of programs, I think around 4,000 across 15 benchmarks. And I have many numbers here. Maybe the most important is this column all the way on the right, which tells you the success rates on our benchmarks. So overall, this is 86%. And these numbers, what does it tell you? It tells you how many of those programs we could successfully classify as equivalent or not equivalent. And so, for example, on filter, you have 99, which means 1% of programs would time out. Everything else, automatically, we can either say that it's correct or it's not correct. This is even better for incorrect programs. So if you only take programs that are incorrect on this set, this success rate is around 99%. Right, there are some more numbers here. So P, for example, tells you the number of submissions per assignments. So you have, on average, 300 of submissions, which is good to test this clustering algorithm. And then the type and complexity of programs varies. So you have lines of code as well. It's around 30 on average. What's also good about this set of benchmarks is that they're mostly correct submissions. Around 90% are correct. That's good because proving equivalence tends to be harder than disproving, so it's good to test this part more. And then there are all sorts of other statistics. So for example, F tells you the average number of functions per program. So you can see that there are programs which consist of a single function, but also more. And on those programs that consist of single function, the success rate is even higher, so it's around 96%, and typically with only one reference solution. All right. So we implemented all of this on top of a Stainless verifier. So Stainless is open source. You also have our artifacts publicly available. You have all the benchmarks there and all those results. I should also mention that there is a lot of great related work in all those 3 areas. So on the topic of automated grading, we are mostly interested in correctness, but there are also those other tools that also give feedback and can repair incorrect programs, a bunch of tools for clustering as well. On the equivalence checking front, I mentioned those tools for regression verification, but equivalence is also there in translation validation, loop optimizations. And then, of course, proofs by induction are not new, right? You have them in many other verifiers and your favorite proof assistants. Okay, I think I can now conclude. So I presented this approach for automated grading that is both practical and rigorous. It's really a combination of simple techniques, right? So there was a bit of functional induction, this function called matching, and clustering. So the approach is indeed fully automated. You just provide as user a reference solution and your submissions, and the rest is done by the tool. The approach is rigorous because it relies on formal verifications. So you have proofs and you have counterexamples. And finally, and maybe most importantly, it is effective in practice. So we tried it on interesting equivalence checking examples, also on real-world programs, and it works there. Thank you, and I cannot wait to hear your questions.
Any questions, please go to here in the middle of the room. There's a microphone there.
Hi, I'm Nadia from UC San Diego. So I think, very cool talk. So I think the most surprising thing about this technique, right, is that you're able to discover these new reference implementations, right, that other programs can then be proved equivalence against. So the reason this is surprising to me is that my intuition is that this equivalence proving succeeds when 2 programs have a similar recursive structure, right, and somehow the structure of helper functions as well. So can you give us an intuition for like how does this happen that, you know, Yes, a program can be, this program in the middle can be similar enough to these and those, but they are not similar between each other. Yes. Like maybe you have the concrete example.
So the question is, those bridges from this picture, for example, it's a bit far, how does this happen, right? So one obvious example would be if the reference solution has a structure such that it hides the recursion. So, for example, here, it was far away, but you had this fold right. So the recursion is not that clear, it's a bit hidden. So if this was our reference solution, then it would not be such a great reference solution. The one on the left would be a better reference solution. I also have a more interesting example that I don't have time to go into details now, but I can put it on the slides while we... Yes, so this is one of the bonus slides. So this is one of the coolest reference intermediate solutions that I found, so I can leave it there. So it's a bit, you have two solutions where one is a bit like tail recursive and the other one is not, and then you have this solution in between that bridges this gap. So it's really about this inductive schema, how direct it is or how hidden it is.
Thanks.
Hi, very nice talk. I'm Jojo from Purdue University. So I have a similar question, maybe the same as an idea. It's about this equivalence definition. So you say one requirements for equivalence about they have same signature. But I can imagine you have a different way to implement an abstract set. It can be a list.
Sorry, could you please speak a bit louder? I'm hearing
okay, so you say one requirement of your equivalence is actually your signature. But I can imagine there's a two way to implement a set. Maybe that is int list or int tree, like binary tree. So, so in general, there's actually have different signature, but somehow they actually have the same semantics. They only want to say there's no duplicate elements in the container. So will you try to say they're equivalent or not?
Yes, so the question was about functions that are equivalent, but they don't have the same signature. So we don't do this for now. This would be one of the extensions that we are also looking at. The reason why we don't really need this in most cases is that you can always say that the signature is part of your problem statement. So this is actually the case for this class, for all those benchmarks. You would have this signature with question marks already defined, and then all students have to keep it. It becomes more interesting when you look at inner functions, those helper functions, where you can have two functions that do the same thing and don't have the same signature. So for now, we did not look into this, but it is very important, and we want to consider this as well.
Okay, thank you.
Hello, Ben Greenman, University of Utah. I'm curious what you do about solutions that are over-constrained. So let's take max, for example. That takes in a list of integers, but if we give it the empty list, a solution needs to choose something, but for a student implementing the assignment, it doesn't really matter what they choose. They could do an error, they could do a sentinel. So what's your take on this?
Yeah, so this shouldn't be a problem. So the question was, so if you have, if I understand correctly, if you have programs that take some subset of the input type, right? So either you can reflect this in types, so you can make a list which is a non-empty list and then use this type, and then this problem goes away. And the second way is with preconditions, which really compose nicely with this technique. And there's a third way, which is to, on top of this post-condition, have some function that will prune out those disallowed inputs and just establish equivalence on the domain that you care about. We actually tried this. It's not a part of this work, but it seems to work well with this approach. It seems to compose fine.
Thank you.
Hi, this is Ravi from Apple. It's a great application of functional verification. So a couple of questions. One, if I understand correctly, you do have cases where you could neither get a counterexample nor be able to verify it. And I believe the model might be that an instructor actually looks at it.
Yes.
Have you tried actually adding it back to the corpus and see how this performs? I'm just curious.
Adding this too?
Have you tried adding this back to the set of reference solutions?
Yes, of course. So this would be maybe the natural flow. So you initially come up with your set of reference solutions, then you run the algorithm, and then for those solutions that time out, so you don't have a counterexample, so they are probably correct, but you still look at them. This will be the natural flow. So you put it back. First, you inspect it in detail. You make sure that it's correct, but maybe just one of them, not the entire 1% or 5%. And then when you're sure that it's correct, you put it back in the pipeline and you use it as a new reference solution.
Cool. Just another question is there are like resource properties that we also want to test, like how good the algorithm is, how efficient it is. So is that a logical next step that you would like to try out?
Other properties such as maybe performance.
Yeah, performance or memory usage.
Right, so we don't really check for this explicitly, so I don't have any numbers there, but I would say that this clustering is actually useful to detect different sorts of solutions. So if you have one tail recursive program and one which is not as a reference solution, then one will assemble all the student solutions that are tail recursive, and one will assemble all the student solutions that are not, as you can give different grades to those.
Cool, awesome, thank you.
Okay, let's thank our speaker again.